Thank you for taking the time to watch this presentation on Nexem railway silencers and how they can provide an effective solution to minimizing the noise generated by trains. We will first examine the details of train noise, and with a good understanding of where the noise is generated, the frequency and intensity distribution of this noise, we will then be able to see how the patented Nexem railway silencer system can provide an effective solution to noise control. So let's get started. While investigating railway sound intensities and profiles, we reviewed much of the research that has been published and available in various relevant journals. We found these two articles shown here to nicely summarize the information and body of knowledge available today. The information in this presentation comes from these two articles and is also supported and confirmed by all the other research reviewed. Let's start by looking at the various parts of a train that generate noise. You have the head of the train, you have this intercoach space between two railway cars, and you have the rear of the train. The car is divided vertically into top, middle, and bottom. You'll see all this more clearly on the next slide, but the bottom is considered as the first 1.25 meters of height starting at the top of the rail. The middle is the next 1.7 meters of height, and the top is the final 1 meter of height, taking you to a total of 4 meters high. Now within the bottom section is a special area called the bogie or trailer. This is the wheel assembly and drive motor of the train. On top of the rail car is the pantograph. This is the assembly that rides on the electrified catenary wire above the rail line and takes the electricity from the wire to provide power to the train. This pantograph rises and lowers as it rides on the wire and can extend from 1 meter above the top of the car to 2 meters above the top of the car. Now, based on the research and sound data collected, when all the sound generated was measured, you can see in this pie chart here that the bottom area, including the bogie, is responsible for over half, 55% of all the sound generated. If you include the middle section of the car, you'll see that these areas are responsible for 79% of the total sound generated. Here we see the sound intensity profile along the height of the train. And as you can see, the bottom of the train is not only responsible for the majority of the sound generated as we saw in the previous slide, but it is also responsible for the highest intensity or loudest sound as well. The middle section, although significant as a proportion of the total sound generated, is not significant with respect to intensity and is actually the least intense of all the sound generated. So it becomes clear based on these two factors that the bottom of the train should be the focus of any sound attenuation activity. Now that we have identified the area of the train that is most significant for noise generation, it is just as important to identify the critical frequencies that should be targeted. In this graph, we see the intensity or sound as a function of frequency. The lower frequency sounds are the highest intensity, and therefore should be the focus of our attention. Here is a more detailed picture of the sound profile that is generated by trains. In the first two graphs, you can see how sound intensity of train noise varies with frequency. The first graph is a close-up view of the frequency range between 0 and 8,000 Hz, whereas the second graph is a full spectrum frequency and corresponding sound intensities. So when we look at the first graph here, the blue is the actual sound generated. And again, you can see the lower frequencies have higher sound intensity. The red is called the A-weighted sound pressure level. This is a modification correction to the measured sound intensity that takes into account the sensitivity of the human ear. We are less sensitive to really low frequencies, less than 125 Hz, and so the A-weighting process puts less importance on these frequencies by lowering the effective sound intensity. What we can take from this is that the frequency range from about 125 Hz to 1000 Hz is the frequency range of most importance when trying to provide a solution to reduce the noise generated by trains. The last graph on the slide actually measured the overall sound intensity generated as a function of train speed. As you might expect, the faster the train travels, the higher the sound intensity. The blue again is the actual sound intensity measured, whereas the red has been corrected to take into account the frequency sensitivities of the human ear. So what we can ultimately take away from this research is that the majority of the sound generated by a train comes from the bottom 1.25 meters of height. The bottom area sound is also the most intense or loudest, and that it is the sound in the lower frequency range between 125 Hz and 1000 Hz that are the most intense and loudest and should be the focus of sound attenuation. So now let's talk about the Nexum silencers and how they work. So what is a Nexum silencer? The Nexum silencer is a patented modular sound panel that is installed at the rail level on the railway bed, either a concrete slab or concrete ties. It is designed to absorb sound directly at the target noise source, which has been identified as the bottom area of the train. Ideally, they are installed on both sides of the rail to capture all of the bottom area sound and not just the portion of sound that is directed straight vertically downwards. Although the concept of a railway silencer isn't new, I'll explain what is new about the Nexum silencer on the next slide. Here is a picture of our silencer. As you can see, there is an outer Nexum cement bonded wood fiber volume that completely encases this inner volume, which can be left empty, in which case it is air, or as shown in this picture, the inner volume can be filled with lower density sound absorbing material. By combining the different materials of different densities and thicknesses, we are able to target those lower frequencies that we identified of being the most important when it comes to trains. The dimensions of the silencers along the length of the track is always 305 millimeters or 12 inches. The height of the silencer can range anywhere between 100 millimeters and 250 millimeters. And the width as it sits between the rails is 915 millimeters maximum, or 36 inches, which is also usually the maximum space available. And then depending on the application, this dimension can be changed, lowered, to accommodate the space available. Here we have a list of the various silencers that are available. RS stands for railway silencer. 100 stands for the total height of the unit, so the RS 100 would be 100 millimeters high or 4 inches. The 915 designation refers to the width of the unit, which is really the space between the rails that is available to have a silencer. We go 100, 150. These are both solid silencers with no cavity. Then we have the 200A. The A refers to the presence of an air cavity, and AP is air plus, where the cavity is filled with sound absorbing material. So you can see on the AP, the overall height is 200 millimeters, the top layer thickness is 100 millimeters, the cavity thickness is 50 millimeters, and again, the AP designation indicates the cavity is filled with lighter density sound absorbing material. Before we explore the sound absorption performance of the Nexum silencers, we need to talk a little bit about how sound absorption of a material is measured, tested, and reported. There are 3 ways to report sound absorption: NRC, noise reduction coefficient, SAA, sound absorption average, and alpha W. In all 3 methods, the result is reported as a number between 0 and 1, with 1 meaning 100% of the sound is absorbed. NRC is the traditional, oldest, and most common. It is an average of sound absorption at 4 frequencies between 250 and 2000 Hz. The SAA is more recent and measures sound absorption averages at 12 frequencies over a wider range of frequency between 200 and 2500 Hz. This is considered better as it has more data points, 12 versus 4, and over a wider range of frequency. Then there is the alpha W. This is a fairly complicated calculation that is still based on the measured sound absorption of the material, but it is also weighted to be more representative of frequencies sensitive to the human ear. It uses the most data points over the widest range of frequency when compared to the other 2 methods. So here's the sound absorption performance of the various Nexum silencers. For the moment, we will only look at the alpha W, as we saw it is the best measure of a material's ability to absorb sound. Also, as noted in this slide, The alpha W method also has a shape indicator that provides additional information about whether the material is particularly effective at absorbing low, medium, or high frequencies. So knowing that we are interested in low frequency sound absorption when it comes to train and railway noise, in order from least to most sound absorptive, we see that the RS100 has an alpha W of 0.7. Then the 250A, which would be 250 millimeters high with an empty air cavity, has an alpha W of 0.78. Then it would be followed by the RS150, which you will see in the following graphs isn't as effective as the 200A despite having a higher alpha W because of the low frequency shape indicator that is obtained with the 200A. Then after the 200A, we have the 200AP, which would be 200 millimeters high, and the cavity filled with low density sound insulation material. And then finally, we would have the 250AP, which again is 250 millimeters high and has sound insulation material in the cavities. Now let's look at the more important silencers in more detail. First, we have the RS150, a solid Nexum silencer, 150 millimeters high and no cavities. We have identified the critical frequency range from train noise that we want to target as between 125 to 1000 Hertz, with special focus on the lower frequencies in that range. And we will look at how the silencers perform in this target range only. We aren't as interested in the higher frequencies as previously explained, even though they all perform extremely well at the higher frequencies. We have also identified subjectively the sound absorption of 0.6 as a minimum base absorption that we would like to achieve. This value of 0.6 was chosen as in most applications, acoustical consultants and specifications ask for a minimum value of 0.6, whether it is NRC, SAA, or alpha W. We have also identified the sound absorption level of 0.8 as a higher level signifying superior performance. As you can see here, the RS150 isn't too bad with respect to the 0.6 level and covers a lot of the target frequency. It covers frequencies from about 200 Hertz and up. You can also see that at the 0.8 level, the range is more narrow and not as effective, only covering frequencies from about 250 to 600 Hertz. Then we have the 200A. It has a better 0.6 absorption range, starting from about 150 Hertz. Again, the 0.8 absorption level is narrow, but the frequency range at this level is lower, covering frequencies between 175 to 475 Hertz. Next, we have the 200AP. It provides the minimum 0.6 sound absorption for the entire frequency range, starting at 0. With respect to the 0.8 absorption level, it is a much wider range starting from about 125 Hertz extending all the way to 500 Hertz. And then finally we have the 250 AP. It provides both 0.6 and 0.8 minimum sound absorption for the entire frequency range starting at 0. So in summary, the alpha W method of reporting sound absorption is better than either the NRC or the SAA, and this should be taken into consideration when trying to understand different materials tested using different methods and their relative performance to each other. Even better than the alpha W is to specifically look at the critical frequency range that you want to target and evaluate a material's sound absorption profile against this critical range. Using this method for evaluation, we see that we should consider the Nexum RS150, then the 200A, followed by the 200AP, and finally the 250AP in that order. So now let's look at the silencers and how they're installed. Here is a table of the Nexum silencers and their weights for 3 increments of width. This is important to keep in mind when considering the installation process. All Nexum silencers are typically installed by hand, and once the silencer reaches weights over 50 to 55 pounds, you will require 2 people per silencer for handling an installation. As you can see, all of the 915 millimeter wide units fall under this category and would require 2 people minimum for installation. When it comes to how the silencers are placed and oriented along the rail line, the 2 main factors to consider are, first, whether the rails are installed on a solid concrete slab or on railway ties, and secondly, the amount of physical space available on the outer side of the rails. Let's start with a concrete slab railway bed. The optimal configuration would be having the railway silencers with the 305mm or 12-inch module length running along the length of the rails. This allows the cavity openings in the silencers to connect with each other, keeping the cavity enclosed, which keeps the inner sound insulation material protected. This is really only of concern with the AP configuration. This orientation is also preferable from a sound absorption perspective. The wider area on the outside of the rail line will absorb more sound that is emitted from the bottom 1.25 meters of train height and hence be a more effective solution. If there is not sufficient space on the outside of the rails, the silencer can be oriented at 90 degrees as shown, so that the silencer is oriented with the longer dimension running along the rail line. The cavities are now exposed to the elements, and although it isn't an issue for silencers other than the AP silencer option requires some additional modifications that will be shown on the following slides. Here we see the 2 previous configurations in an end or section view. Each silencer is laid down and fixed to the concrete base with standard exterior construction adhesive, typically at 4 points per silencer. In the case of the installation with limited space on the outside of the rails, the outside silencer cavities need to be capped with the Nexum cavity caps to protect the inner sound insulation material. Again, this is only required if using the AP silencers. Also, if required, and as shown here, you can overhang the silencers past the edge of the rail bed if required to achieve the necessary clearance from the rail and rail attachment assembly. This is a side view of the silencers that are running on the exterior outside of the rails. As shown here, even with the optimal configuration, you will still need to cap the cavities at the end of each run. This can be done as shown here with a cavity cap strip, or alternately, you can replace the last silencer in the run with a solid unit. So for example, if these were all 200 AP units, the end units would just simply be the RS200 solid units without the A or AP designation. Now let's look at the installation of silencers on a rail line that is installed on concrete ties instead of a flat concrete slab. In this case, the silencers need to be installed with the long dimension running along the length of the rail line. This would be required for both the interior space between the rails as well as the exterior space on the outside of the rails. Also, the long dimension of the silencer needs to match the tie spacing, which is typically 30 inches or 762 millimeters. This dimension would be specified, and we would custom manufacture the appropriate size silencer to ensure that they can span from railway tie to railway tie. Here is the end or section view as seen at a concrete tie, as well as the side view of the exterior silencer spanning between concrete ties. The cavity cap strip would be required here if using the AP option. These strips would either be installed on site or they can be pre-installed at the time of manufacture and delivered to site as one piece. Again, where required, the exterior units can overhang the tie for clearance purposes. And what is different when installing on concrete ties is that you only fix the silencer to one tie and not both. This would allow for any movement or thermal expansion and contraction to occur without splitting or cracking the silencer over time. Another point that is important to consider is the flexibility available with Nexum silencers. We can customize the silencer shape, dimension, and cavity sizes to suit the specific needs of any project. In this example, we have designed a modular silencer that allows for different dimensions of coverage based on multiple different space requirements on either side of the tracks. This unit can be installed as per normal and cover a width of 508 millimeters or 20 inches. Also, you can cut the unit down the middle to create two separate 10-inch units. This cutting can be done on site with simple carpenter tools like a skill saw, or upon request be pre-cut at the time of manufacture prior to shipping. With the optional 10-inch module, you can now cover either 10-inch, 20-inch, 30-inch wide spaces on either side of the tracks. And that concludes this presentation. Once again, we appreciate your taking the time to watch. Thank you.